Today, we are mastering the factor and remainder theorems for the Cambridge Pure Mathematics 3 exam. These theorems are essential for handling high-degree polynomials, allowing us to find remainders, identify factors, and solve cubic or quartic equations without always relying on tedious long division. In the P3 paper, you will frequently use these to find unknown coefficients, or as the first step in solving a complex algebraic problem. We will begin with the remainder theorem, then progress to the factor theorem, and finally apply these to exam-style questions involving simultaneous equations and polynomial solving. The remainder theorem states that when a polynomial p of x is divided by a linear divisor of the form ax plus b, the remainder r is given by evaluating the polynomial at x equals negative b over a. The remainder theorem is a powerful shortcut. Usually, to find a remainder, you would perform polynomial long division. However, the theorem states that if we divide a polynomial, p of x, by a linear divisor of the form ax plus b, the remainder r is simply the value of the polynomial when we evaluate it at x equals negative b over a. Mathematically, we can write any polynomial as the divisor times a quotient, q of x, plus a remainder, r. If we want to isolate r, we can make the divisor term 0. By substituting x equals negative b over a into the equation, the entire term containing the quotient disappears. Substituting this value in, the divisor becomes 0, which multiplied by the quotient is 0. This leaves us with the remainder. This is why the theorem works. It uses the 0 of the divisor to bypass the division process entirely. Let us look at a quick example. Find the remainder when p of x equals x cubed minus 2x squared minus 5x plus 6 is divided by x minus 2. According to the theorem, we set the divisor to 0. X minus 2 equals 0 gives us x equals 2. Now, we substitute 2 into our polynomial. The remainder r is 2 cubed minus 2 times 2 squared minus 5 times 2 plus 6. Expanding this, we get 8 minus 810 plus 6. The remainder is negative 4. Notice how much faster this is than setting up a long division table. In the exam, saving this time is crucial for tackling more complex parts of a question. The factor theorem is simply a special case of the remainder theorem. It states that a linear expression, ax plus b, is a factor of the polynomial p of x if and only if the remainder is exactly 0. This makes logical sense. If something is a factor, it divides into the polynomial perfectly with nothing left over. Visually, if ax plus b is a factor, then x equals negative b over a is a root or x-intercept of the graph. Looking at the graph of our previous polynomial, we can see it crosses the x-axis at x equals negative 2, x equals 1, and x equals 3. Because the function value is 0 at these points, we know that x plus 2, x minus 1, and x minus 3 are all factors of that polynomial. In P3 exams, you will often be asked to show that a linear term is a factor. All you need to do is show that substituting the root results in 0. Let's solve a typical P3 problem. The polynomial p of x equals 2x cubed plus ax squared plus bx minus 6 has a factor x minus 2. When p of x is divided by x plus 1, the remainder is negative 12. Find the values of a and b. First, we apply the factor theorem. Since x minus 2 is a factor, p of 2 must equal 0. Substituting 2 into the polynomial, we get 2 times 2 cubed plus a times 2 squared plus b times 2 minus 6 equals 0, which simplifies to 16 plus 4a plus 2b minus 6 equals 0. Simplifying this gives 4a plus 2b equals negative 10. We can divide the whole equation by 2 to make it simpler. So our first equation is 2a plus b equals negative 5. Next, we apply the remainder theorem for the second divisor. Since dividing by x plus 1 gives a remainder of negative 12, p of negative 1 must equal negative 12. Plugging in negative 1, we have 2 times negative 1 cubed, plus a times negative 1 squared, plus b times negative 1 minus 6 equals negative 12. This becomes negative 2 plus a minus b minus 6 equals negative 12. Collecting like terms, we get a minus b minus 8 equals negative 12. Adding 8 to both sides, we get our second equation. Now we have a system of simultaneous equations. To find a and b, we solve the two equations simultaneously. We have our first equation, 2a plus b equals negative 5, and our second equation, a minus b equals negative 4. The easiest way here is elimination. Since we have a positive b and a negative b, we can simply add equation 1 and equation 2 together. Adding the left sides gives 3a, and the right side gives negative 9. Dividing by 3, we find that a equals negative 3. Now that we have we substitute it back into equation 2 to find b. Replacing a with negative 3, we get negative 3 minus b equals negative 4. Adding 3 to both sides, we have negative b equals negative 1, which means b equals 1. So our final coefficients are a equals negative 3 and b equals 1. This type of question is very common in the early parts of a P3 paper, often worth 5 or 6 marks. Always double-check your arithmetic when substituting negative numbers, as that is where most marks are lost. Once you have identified factors, you will often be required to solve the equation p of x equals 0. This involves 3 key steps. First, use the factor theorem to find at least one root. If the question doesn't give you a starting point, test small integers like 1, -1, or 2. Second, divide the polynomial by your known factor. This reduces a cubic polynomial down to a quadratic quotient. Finally, factorize the resulting quadratic using the quadratic formula or inspection to find the remaining roots. Remember this summary. If the divisor is x plus b, just evaluate p of negative b, but if there is a coefficient in front of x, like 2x plus 3, you must evaluate p of negative 3 over 2. Let us examine some common pitfalls students encounter in P3 examinations. The most frequent mistake is using the wrong sign when substituting into the polynomial. If the divisor is x minus 3, you must substitute positive 3. Students often substitute negative 3 by mistake. Remember, you are substituting the value of x that makes the divisor 0. When applying the remainder theorem, students sometimes set the expression to 0 as if it were a factor. If the question states the remainder is 5, ensure your equation is p of c equals 5, not 0. For a divisor like 2x minus 1, many students try to substitute negative 1. You must solve 2x minus 1 equals 0, which gives x equals 1/2. Always verify your root before substituting. When evaluating terms like ax squared or bx cubed with a negative x value, students often confuse the signs. Remember that a negative number squared is positive, but a negative number cubed remains negative. Use brackets on your calculator to avoid this. To secure top marks in your Cambridge P3 exam, keep these professional tips in mind. First, show the substitution step clearly. Even if you are using a calculator, always write down the polynomial with the substituted values. If you make a small calculation error but have shown the correct substitution, the examiner can still award method marks. Next, use the ANDS button on your calculator. To avoid repetitive typing and sign errors, type the value of x, press equals, and then type your polynomial expression using the ANDS key. This is a much faster and more accurate way to test multiple potential factors. Always read the wording carefully. If a question says exactly divisible by, it means the remainder is 0. If it says leaves the same remainder, set the two polynomial evaluations equal to each other. Verify your factors. If you find that x equals 2 is a root, the factor is written as x minus 2. A common mistake is to write x plus 2. Always perform a quick mental check. Does my factor equal 0 when I plug in my root? Finally, look for the hence command. In Cambridge papers, the word hence means you must use your previous answer. If you just found the values of a and b, use those specific values to solve the next part of the equation.